Okay, so this is the answer key and kind of going over the assessment review. So hopefully you've already practiced. And if you had questions, then you are using this to double check your work and that sort of thing. So first of all, the first question is related to numbers of possibilities. So at the end of the student council meeting, students have a snack and a drink. Each student may choose only one snack and one drink. The snack choices are chips, pretzels, cheese crackers. So for those of you who needed that clarification, it's one in this particular case, no comma, and then or cookies. So you have a total of 4 choices. Okay? And certainly that clarification was valid because it did not transfer well to the last assignment. It changed where the comma was. So I understand and certainly would have made a difference. Okay, the possible drinks now are there 5 possible drinks: orange pop, cola, Gatorade, red pop, or milk. So 5 possible. Okay, now anytime that does happen, as long as you show me all your work, I'm going to give you both answers correct. So if it's how many total combinations of one snack and one drink, so I am going to take what seems like the simplest way, 4 times 5, which is 20 total possibilities. Okay, now this also says show another method. Now I like tree diagrams more than writing long lists, but I will first give kind of a key for what my tree diagram is going to look like. So I'm going to start with my chips, my pretzels, my cheese crackers, and my cookies. So I'm calling cheese crackers CC and cookies CO because I have so many snacks that begin with the letter C. So I'm just going to start with C, and then I'm going to draw 5 different lines out of the C because I could choose that chips, and I could also choose 5 drinks with that. Okay, and I'll label them in a minute. So I'm going to do the same thing with pretzels, and 1, 2, 3, 4, 5. Same thing with cheese crackers. 1, 2, 3, 4, 5. And same thing with cookies. 1, 2, 3, 4, 5. Okay, and then I'm just going to label all of these, and I'm going to choose a different color just to clarify that for you. Obviously, you wouldn't have to do all of this. So orange pop, cola, Gatorade. I'll use C again because it's going to be in a different spot. And red pop and milk. So I'm just going to basically write that O, P, C, G, R, P, and M. And the same thing every time. It doesn't really matter if you did it exactly the same way, as long as I can see all of the possibilities. O, P, C, G, R, P, and M. And the same thing here. O, P, C, G, R, P, and M. And you can see, let's move that up. There you go. You can see now, like if I counted out all of these blue letters, 5 here, 5 here, 5 here, and 5 here, I'm going to get a total of 20 again. Okay, now this will be useful because now I have some questions that specifically are asking about probability related to this. So now that I've done all of this work, I can just use it to show my answers rather than rewriting an explanation every time. It's still showing work. So it says, what's the probability the student will choose cola and chips? Well, here's cola and chips. So I'm going to highlight this one in yellow to show my work. So in yellow, we know our total was 20. And there was only one option out of the 20. So above in yellow, or you could draw an arrow, or as long as I can see kind of what you're talking about. Okay, so there's 1 out of 20 and you're done. So now I'm going to do this next one. Probability a student will choose Gatorade. I'm going to do that in pink to make it obvious I'm looking at different things. Gatorade is here with a G. So right there, right there, right there, and right there. Bless you. And this one is 4 out of 20. Or 1 in 5. And it shows up above in pink. Okay. Yeah, you should reduce your fractions if it's possible to reduce. And you could have also found that obviously different ways because there were 5 drinks and Gatorade is 1 out of the 5. So there are other ways to do all of these problems. I'm just showing you one option. And just remember to show work. That has definitely been an issue. And on the assessment, it will matter. All right, so read these questions carefully, because experimental and theoretical probability, you really do have to read, if it's a scenario, what's happening. So it says there's 3 doors that may possibly have prizes behind them. The game contestant, Connor, has to pick one door to try to win the prize. There's a 1/3 chance that he picks the door with the prize. Clearly, so far, he has not actually picked. It just says there's a 1/3 chance. So this is a theoretical probability. Okay, this is based on math. So he hasn't actually done an experiment or picked. Okay, it's based on mathematical odds. Okay, you don't necessarily have to say all of that. You could just say he hasn't actually done he hasn't done any sort of process that would make it experimental. Okay, now the second one, Enza and Tatiana roll a pair of dice 25 times. So they actually do the experiment. Okay, they roll a sum of 10 3 times, and they use this data to predict that they will roll a sum of 10 12 times if they roll it 100 times. So this is an experimental probability, just because based on, so their prediction was based on an experiment or a process, not based on mathematical odds per se. Okay, now this question can be a little confusing, but it will be pretty much the same question because I want you to understand how theoretical and experimental probability relate to each other. So will they always be the same or different? The technical answer to this is neither. Like, they can be the same and they can be different. But what I want you to understand is as we increase the number, as the number of trials increases, experimental probability will approach theoretical. And eventually they'll be the same. Because eventually you kind of just work out those odds. You've done it so many times that you're eventually going to, if Enza and Tatiana rolled this 3,000 times, eventually they're just going to, the odds say that they're going to hit all those numbers closer to 1 in 6 times. Okay, so it approaches the theoretical as the numbers get increasingly bigger. Okay, so they can be the same and they can be different. It kind of depends on the number of times. They're more likely to be the same if your number of trials is larger. Okay, so in the spinners below is it equally likely that you land on each color? And then just explain. So here I can see that blue, orange, and yellow are the same size. You don't have to prove they're the same size. If they're pretty clearly the same size, you can just say they have the same size or the same area. So yes, this is equally likely. And that's because each is the same size. Has the same size or area, or however you want to, I'll say area. Okay, because it is kind of an area model. You can say size, area, that's fine. Okay, here, is it equally likely? No, yellow is clearly larger than blue. Okay, there are multiple ways you could explain that. I just want to know that you understand the concept of something being equally likely. Okay, and in most times when we're talking about theoretical probability in this class, we are assuming equally likely events. Right. Next question is about 6-sided dice. So always assume, by the way, that if I'm talking about 2 dice, so 6-sided number cubes, that I am talking about fair dice. Okay, because if I'm talking about unfair dice, then you really can't figure out the answer. So remember, 6-sided dice means that each die has a number from 1 through 6 on it. All right, so I'm going to label them in different colors. So green will be my first die. Okay, and purple is going to be my second one. And then I'm just going to make a list. Now, I like to make my list organized so I don't lose track of things. So I begin with the first die, and I just list I could have 1 happen on the first die. And I listed that 6 times because now I'm going to list the second die as the other option. So I could have a 1 1, a 1 2, a 1 3, 014, 015, or 16. Okay? So I could also do the same with a 2 on the first die. Okay, a 3. F4. Oops, excuse me. 4, 4, 4, and 4. And a 5. You don't want to go too quickly because that error I was just about to make will happen. Okay, and options of 6. All right, so now I'm going to list the other ones. So these are all my possible options. Okay, and then I'm going to just use a highlighter to determine the actual outcomes that fit my answer. Okay, so I kind of got off track on that set, so I'm just going to clarify that those are 3 different ones there. Okay, so now it says, what's the probability of getting a sum greater than 8? Now, if you count all of these out, there are a total of 36 possibilities, 6 in each row. So my total is 36. So I'm going to do this in fraction form, and then it says sum greater than 8. So I'm just going to highlight again my sums that are larger than 8. There is nothing here that is larger than 8. 1 plus 6 is 7, so none of the ones equal anything larger than 8. 2 plus 6, it says greater than 8. It doesn't say greater than or equal to, so 2 plus 6 is not, and all the rest of these are smaller. 3 plus 6, however, is 9, so this one is larger than 8 when I add the 2. Remember, sum is adding. Okay, so I'm adding there. 4 and 6 is 10, so that's greater. 4 and 5 is 9. 5 and 6, 5 and 5, 5 and 4, those are all greater than 8, but this one's just 8. And then those sums, those 4, are all also greater than 8. So, if you notice, now I'm just going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now it's 10 out of 36. I would like you to reduce the fraction if you've done all that work and you happen to forget reducing the fraction. I'm not going to worry about it. You definitely have the idea, but the reduced fraction is 5 and 18. Okay? Wouldn't necessarily be reducible. All right, next question. So Jacob's teacher brought in a bucket containing 90 blocks, some red, some yellow, and some blue. And Jacob wanted to figure out how many of the blocks were yellow without emptying the bucket. He drew a block from the bucket, recorded the color, and then he replaced it. And he did this 25 times. So of his 25 draws, 11 were yellow. So here's our experimental probability. 11 out of 25 are yellow. Okay? Now based on his experiment, we need to approximate how many of the blocks are yellow. So we know there's a total of 90 in here. And on this one, I'm going to use a calculator because, of course, I thought I grabbed it, but I didn't. So I know this one isn't going to be exact. Oh, unfortunately, the cat sat on it. So anyway, so this one's not going to be exact. So this is a proportion problem, and so you can kind of make a choice as to which direction you want to go. I can look at 90 divided by 25. Okay, and that says 3.6. So if I go kind of like this was multiplied by 3.6. Okay, now if I take 11, okay, I get 39.6. Well, obviously I can't have 39.6 blocks there, so I'm going to say that's around 40. Okay? Now, if you go the other direction, you choose the 11 and the 25, that would also work. So if I did, for example, 25 divided by 11, okay, but that number is not nearly as pretty, so I'm probably going to stick with the number I have. Okay? So you could use that number, and these are approximations, so remember if you're off by 1, as long as you've rounded it correctly and you've shown all your work, that's fine. Next question. So Hannah and Cassidy are analyzing a game involving two different spinners. To help them find theoretical probabilities, they made the counting tree shown. So you've got this whole counting tree, and here you need to list all the outcomes. And this is going to help you later on because then you're going to be able to just use that. So I'm not going to make a key because red and blue and green and yellow, I'm just going to use the first letter, and then these are just numbers. So, and you've done this, a similar problem on your homework, so it's kind of simple, but take your time. So I'm writing it as blue 1, blue 2, blue 3, and there's another blue 3. So the spinner of some sort has an equally likely chance of landing on 3 twice. So either it's double the area or there's 2 blocks with the 3 in it. I'm going to go with the 2 blocks. So the second one is red 1, red 2, red 3, and red 3. But you have another option of red on the first spinner. Okay, and then you've got a green 1, green 2, green 3, green 3, and same with yellow. Okay, again, the point being that there are multiple ways to look at probability, but generally a lot of it is organized counting, at least early on. Later on, there are shortcuts for a lot of things. So red on spinner A and 3 on spinner B. So you have to do both, okay? And implies both things. So red on spinner A and 3 on spinner B. So here's red on spinner A and 3 on spinner B. Okay, so that happens 4 times. Now the total, there were 4, 8, 12, 16, 20 ways. So this is 4 out of 20. Okay, and then I can also show the reduction of 1 in 5. Okay, but my work is shown up there in yellow. Okay, not getting 3 on spinner B. So I'm going to now circle my answers instead of highlighting because I'll kind of just show where that is. So again, kind of any way you show work, as long as you're showing work, is perfect. So not getting 3 on spinner B. So here's these 2, these 2. So you can kind of even see it's half of the overall area. So you could have just written half, or if you didn't do that and you wrote 10 and 20, that's fine as well. So not getting 3 is 1 chance out of 2, or 10 out of 20. All right, so the computer is now hiding a random treasure. So you've seen this one as well because it's an area model, and I really like this area model because it kind of shows a clear idea of what area models can look like and uses equally sized squares, so there's an equal likelihood of landing in any square. Okay, so if we counted all of these, it would be 100. And we've done this before, but this is 10 and this is 10, so 10 by 10 is 100. Okay, so the total number was 100. Okay, and I am going to count the Great Hall. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 21, 22, 23, 28, 29, 30, 32. Okay, 42 out of 100 chances. Now, if you'd like to reduce that, that's great, but I'm going to leave it here. So it was the Great Hall out of the total. If you reduce it, that's fine. It's 21 and 50. I'm not going to be looking for a reduction there. Partly because I think it's easier if I am predicting based on a proportion. In this case, because it was out of 100, I can see that 42 out of 100, if I were to play 200 times, I would multiply this by 2. I would expect this particular situation to occur in the Great Hall 84 times out of 200. My answer is actually 84 times. That's the expected number. That's not necessarily what will happen, but that is the expected based on, in this case, theoretical probability. Okay, last question, and I want to clarify because I don't think that number is super clear, so I'm going to write this number outside here. So that space is 350. Okay, what's the probability of landing on 400 or more in one spin? So each one of these is the same size. You don't have to measure to double check. So there's 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 total possibilities. So this is out of the total. And I'm just kind of showing work. If you had dots on it or like showed me that you counted in some sort of way, that would be work as well. So I'm just writing total. So you know it's 10 total possibilities. Now, 400 or more. So I'm going to highlight the ones that are 400 or more. 350 is not. 1,000 is. 400 is because it's 400 or more. So that includes 400. Bankrupt is not more than 400. 200, no. 750 is. 300, 100, 250, all no, but 500 is. So you'll notice I came up with 4 of them. You can also reduce that fraction, although as we didn't do a whole lot of practice with reducing fractions, I'm not as concerned about it. So 2 chances in 5. Okay? So bankrupt in 1 spin. Again, still just 1 spin, so the total is still the same of 10. And the answer is 1 out of 10. So there's 1 bankrupt. I'll just circle it up here so you can see. And the 10, I've already kind of shown work for that. I already said it was a total. It's the same spinner. So showing work would be fine to circle. All right, so hopefully that is something that you're comfortable with. So the assessment will be assigned actually next week after you've gotten a chance to do all the practice. Have a lovely day.